Okay, we're going. The other day, yesterday, I think, I mentioned the tsunami that happened in 2004. Thought it was 2006, but it was the coast of Sumatra, not Indonesia. And there's a problem in the book about this. Um, it actually killed 200,000 people, so it was even more devastating than I'd remembered. But satellites observing the waves from space measured 800 kilometers from one wave crest to the next, and a period between waves of 1 hour. So, what was the speed of the waves in meters per second and in kilometers per hour? It's actually easiest to get in kilometers per hour. And if you just figure looking from space, the satellite would see these wave crests in the ocean, and 800 kilometers from one wave crest to another. And the wave period was an hour, the period between waves. So if you picked some location like right here, where the wave happened to be passing at some instant, it would take an hour for the next wave to get there. And that means it's traveling at 800 kilometers per hour. So the speed of that thing was 800 kilometers per hour. Interesting thing about these waves, they were the amplitude when they were far out from the shore was not very great. Might be just a foot or so. And there were fishing boats that weren't too far offshore from where the waves came ashore that just felt a slight rocking when the waves went by. The actual ordinary ocean waves were different. However, they were going a whole lot faster than regular waves, and that was part of why they were so devastating. But when they came ashore, their amplitude increased tremendously, and that's what made it so bad. But anyway, with that speed of 800 kilometers per hour, you can convert that into meters per second, multiply by 1 hour over 3,600 seconds, and then 10 to the third meters over 1 kilometer. And you can find out how fast they're going in meters per second. Let's see. Um, yeah, I get about basically, let's see, we probably only got one significant figure, but I get 222 meters per second. But um, at any rate, to one significant figure, 200 meters per second, which is pretty darn fast. So that's about 40 meters per second is about 90 miles an hour. And it'd be about 450 miles an hour. So pretty quick. And then let's see, speed of the waves. Yeah, we've got that. That's part of what can cause so much destruction. And then the amplitude when it went ashore. And I mentioned yesterday with a period of 1 hour, that means for half of that period, the wave's going to be falling. And then for the next half, it'll be rising, a continual rise for half an hour of the water height. So that was part of what made it devastating. Okay. Um, we're going to consider a bunch of different things. This is a problem that we could have maybe done yesterday. Well, not quite, actually. We're going to have to hold off on this one. I haven't introduced the wave equation yet, but I will. Um, this is something that I often do the first day of class. And it's a series of problems that are just kind of drawing problems where you draw a bunch of different things. And I've got this file on the page that I'm working on for today's class. I'm not all the way done with it yet, but there are a bunch of different just drawing exercises you can do. And they're kind of challenging in a way to try to get them right, but sort of interesting too as to what happens with waves. But anyway, we've got a little wave pulse here, and it's traveling to the right at 2 meters per second. And then down here, I'm supposed to, oh, by the way, this is a Y versus X graph. So showing the vertical displacement of this wave at different points. And then this pulse is moving along here at 2 meters per second. But below that, you're going to show a Y versus T graph at this particular point on the axis. And so we're supposed to imagine what that's going to look like. Well, here's the leading point of the wave. At time 0, it's at this point 4 meters to the right here. How long will it take to reach that point out here at 8? Well, since it's 4 meters and it's going 2 meters per second, it'll be 2 seconds before anything happens out here at 8. So for the first 2 seconds, that thing out there at 8 meters is just going to sit there like that. And then there's, let's see, this would be 2, 3, 4. There's a 1 meter stretch where the wave is descending, or the medium is going to be displaced downward. Well, that's 1 meter. That's only going to take half a second for it to drop down here to minus 2 meters. So here's 2 seconds, here's 3 seconds. For half a second, that's going to drop down there at that location. And then for the next half second, it's going to rise up. And this point will then have reached the 8 meter point. And then for the next half seconds, it's going to continue to rise up to 2 meters. Then for the next half second, it'll drop down again. And I'm figuring out all of these things because it's 1 meter between these different events, actually 2 meters between these two, which would take a full second. So that's what's here. And then drops back down there again. Whoops, missed. And then the pulse has passed, and it just goes back to 0. So that's what it'll look like. And it's kind of challenging to do these things for some of these different situations on here. This is a graph that starts by showing what's happening at the x equal 8 meter position. And you're supposed to sketch a snapshot of what the wave was doing at t equals 0 seconds. So this is turning the previous problem on its head. But give these things a try. And then here's a longitudinal wave, which is really kind of mind-boggling to mess around with. So those are just some things to try out. For today, the other day we learned a little bit about wavelengths and things like that. And the ideas like period and frequency. So we found out that V is equal to F lambda for a wave. And there's also, we could talk about a period of a wave, which is the reciprocal of the frequency, or the frequency is the reciprocal of the period. We can go back and forth between these things. And let's see, what else do we have going on? There's also, you can take omega, and that's going to equal 2 pi f, or maybe 2 pi divided by the period. So we'll have that showing up in here as well. And we talked about the different kinds of waves. Now, in section 15.3 of your book, they kind of developed the equation for traveling waves, but it's to really do it right and do it with some mathematics that you could really understand, you'd have to have had a course in partial differential equations. And we don't even teach that class at Big Bend. We have a course in regular or ordinary differential equations, which are one-dimensional, but the partial differential equations deal with multi-dimensional equations, and that's what you have to develop a wave function. However, we can still work with the formula as it's developed, and here's what it looks like in the book. They have a sideways, this will be for a transverse wave. And so y of x and t, in this case, you might have x going this way and y this way. Sometimes we'll turn it on its head. One of the example problems will, or rotate it 90 degrees. But anyway, y of x and t will end up looking like this for a traveling wave. A cosine of kx minus omega t. All right, well, some various things that we can do. We can imagine, what if we let t equal 0? Then this equation, so we take a snapshot of what this wave will look like at time 0. It'll just be a cosine of kx. Well, what's that going to look like? Well, we know what the cosine function looks like. At 0, it's got its maximum amplitude, so it would have an amplitude up here of a. Its minimum displacement is going to be minus a, so we'll have that. It'll drop down here like this. That's not a very good cosine function, but we can kind of sketch it anyway and do something like this, come up here, and this is not one of my better graphs, but anyway, it'll do something like that. Well, this is going to happen when kx is equal to, well, let's see, the cosine function goes to 0 when its argument is pi over 2, so we'll have kx is equal to pi over 2. The complete cycle is going to be when kx is equal to 2 pi, and something that we can see here, this distance from this peak to this peak is actually the wavelength. And so the wavelength is when kx is equal to 2 pi. Well, what does that tell us about these things? X is actually going to equal the wavelength over here at that point. And so k would equal, or k times lambda would equal 2 pi, or that thing k is going to be 2 pi divided by the wavelength. So that's something that we can figure out from this equation. This would be the equation of a wave that's traveling in the positive x direction. Having the minus sign in here ends up shifting it to the right as time goes by. If you had a plus omega t, so kx plus omega t, it would end up being one going to the left. And you could make a bunch of graphs to see that illustrated, but you've probably done things like that in an algebra class. You make a graph that might have some kind of an argument and then change the x value with a minus sign and it'll shift it to the right, or put a minus something in the argument. And you may have done things. But anyway, that's what k happens to be. And k is called the wave number, and that's just something that shows up in these. In some classes, instead of the letter k, they might use the Greek letter kappa, which looks pretty much like it. It's just kind of a compressed K. And you might run across that someplace, but we're just going to use lowercase k for the wave number. But it'll be 2 pi divided by the wavelength. And then omega, you know about, it's 2 pi times the frequency, or 2 pi divided by the period. You could also imagine making x equal to 0. In fact, we could do a graph of that. If you take your cosine of the amplitude, whoops, we'll have y of x and t. Here's the general wave equation, a cosine of kx minus omega t. Let x equal 0, and then you'd have instead a cosine of minus omega t, and this would be y of x and 0. So now you're taking a, whoops, no, it's y of 0 and t. So now we're going to look at how the point where x is 0 changes in time. And what you see that you have here is it's going to have a sinusoidal variation. And actually, any point along the wave, we could have picked any other value of x besides 0. And what it does in effect is put a phase constant on this thing, which with traveling waves, we don't worry because they're moving along and undergoing all this stuff all the time. We don't usually try to mess around with the phase of it. But if you made a graph of that, it's going to be a cosine function, but the negative cosine function. So I just flip it on its head, and it would just keep going on and on. But this time it's going to be a t graph, and this would be the y-axis, and it would have a maximum value of a and a minimum value of minus a. But with motion like this, that point on the string or whatever it is that's traveling is going to be undergoing simple harmonic motion, just going up and down with an amplitude of a, and it's going to have an angular frequency of omega, but it'll have a period that's omega divided by, let's see, omega equals 2 pi f. So omega divided by 2 pi would be the frequency. The reciprocal of that would be the period. But anyway, there's simple harmonic motion going on as this wave passes by. And we picked x equals 0. We could have picked x equal anything along this string or whatever it happens to be. And that point would undergo simple harmonic motion, just not necessarily at the same time, unless we picked the points where we were 1 wavelength away from the origin or 2 wavelengths away. Those would act in concert with that x equals 0 thing. So those are some things that happen with these waves. Okay, so this problem is our first introduction into doing something with the actual wave equation. So anytime you see something, transverse waves on a string, it's got a speed, an amplitude, and a wavelength. And so we can say stuff like, well, y of x and t is going to equal some amplitude, which they gave us, 0.0700 meters. That's 7.00 centimeters. Cosine of kx minus, is it minus or plus? So they travel in the negative x direction. So for that one, we put a plus sign in here and have the omega t. Oh, by the way, since k is equal to, whoops, equals 2 pi divided by the wavelength, and omega, whoops, let's try this again. Omega is 2 pi times the frequency. If you solve this thing for lambda and get lambda is 2 pi over k, and f is omega over 2 pi. This is just a little thing that pops out of these things. We know that the speed of the wave is the frequency times the wavelength. That was something that we did the other day. So frequency times the wavelength there, and that would be omega over 2 pi times 2 pi over k. 2 pi's divide out, and another way of writing the speed is as omega over k. And you can see this wave equation written all kinds of different ways. Instead of k, you might have 2 pi over lambda here. Instead of omega, you might have 2 pi over t, or 2 pi times the frequency. Lots of different mixes that you might see in the way that wave equation could be written. And sometimes it seems as if they're just doing it to confuse you. But be aware of that you could break it down somehow to make it look like kx plus or minus omega t. So what have we got? It's got a wave speed of 8 meters per second, an amplitude of that, and a wavelength of that. They travel in the minus x direction, and at t equals 0, the x equals 0 end of the string has its maximum upward displacement. So what that means is if we set t equals 0, then we just have a equals, or y equals a cosine of kx. To have its maximum upward displacement, there must not be any kind of a phase constant. Sometimes you may see this as a cosine of kx plus omega t, omega t, plus a phase constant. And most of the time, we're just going to ignore that because these are things that are just bobbing up and down continually. So it's just nicer to deal with that. But in this case, it happens to be 0. What they want us to do, find the frequency, period, and wave number of these waves. Well, let's see. One thing we know is that they've got a wave speed of that much, a wavelength of that much, 0.320 meters, and the speed is going to equal f lambda. Well, since we know v, the speed, and we know the wavelength, we can find the frequency easy enough. It's just 8.00 meters per second, v divided by lambda, and divide by 0.320 meters. And the meters will divide out, and what we end up with is per seconds. You can think of the wavelength as being meters per wave. Sometimes that may help you. And if you invert those units and multiply, you'll end up with waves per second, which is kind of what you might expect for a frequency. But at any rate, whatever 8 divided by 0.32 happens to be, and I get 25.0, and it'd be waves per second, or you could just write it as 25.0 seconds to the minus 1, or you could write it as 25.0 hertz. And a hertz is a cycle per second or a wave per second. And so 1 Hz is equal to 1 cycle per second. The cycle is just a placeholder word. You could replace it with wave if you want, but those may look like absolute values, but it's just one. Anyway, there's the frequency. So we know that period then is going to be the reciprocal that. So it'll be 1 over 25.0 seconds to the minus 1 on the bottom becomes seconds on top. And, oh, great. Gave me a fraction, just what I need. Anyway, I should have been able to do that in my head. It's 4.00 times 10 to the minus 2 seconds for the period. So now we know that. The wave number. Okay, wave number, somewhere here I wrote it. It's 2 pi divided by the wavelength. So the wave number looks like 2 pi divided by 0.320 meters. So that wave number has units of inverse meters. Which is, in this case, 19.6. And the units on that would just be inverse, excuse me, inverse meters. So now we've got that. Then write a wave function describing this wave. Okay, well, here's what the wave function is going to look like. It'll just be y of x and t. I just take the numbers I've figured out. Oh, I figured out the frequency. I didn't figure out omega, but I can just stick a 2 pi onto it if I want. Anyway, the amplitude was 0.700 meters, or 7.00 times 10 to the minus 2 meters, or 7.00 centimeters. So there's the A. And then the cosine of, well, K is 19.6 meters to the minus 1 times X. So there's that part. And we've got a plus omega. I guess I could figure just take 25 times 2 pi. And I get 50 pi. Imagine that. Let's see, 1.157. And those would be seconds to the minus 1 times t. It's my wave function. So that wasn't so bad yet. Continuing on with that problem, it asks, find the transverse displacement of a particle at x equals 0.360 meters at time t equals 0.150 seconds. Well, I want to know what y happens to be at that place and time. So all I would do is stick in 0.360 meters for x and 0.150 seconds per t. Let's see how that comes out. It's just, this is just plugging and chugging into the equation at this point. So y of 0.360 meters and 0.150 seconds will be the cosine of all this jazz, 19.6 meters to the minus 1 times 0.360 meters. Just plugging and chugging on here. Notice that when those two things are multiplied together, you'll have a dimensionless quantity, which is what a radian happens to be, is a dimensionless quantity. And then plus 157 seconds to the minus 1 times 0.150 seconds. And again, that's a dimensionless quantity. By the way, we could call this radians per meter, and we could call this radians per second, because that represents omega. And but a radian is just a placeholder word. It's dimensionless. Anyway, you'd end up with something or other. I'll just plug it in and see what it is. Oops, clear. The greatest danger on a problem like this is just hitting a wrong number with your finger. I get about oh, I forgot the A in here. It's supposed to be 7.00 times 10 to the minus 2 meters. I have to multiply by that. So and I get 4.83 times 10 to the minus 2 meters, or 4.83 centimeters. So just plugging numbers into this equation is all I'm doing. Okay, let's see. How much time must elapse from the instant in part C until the particle at x equals 0.360 meters next has its maximum upward displacement? Okay, this one's going to be a little bit trickier, but we do have this equation to describe what's going on here. Now, right now, we don't even know if this thing is going up or down, right? All we know is that it's got a positive displacement at this time at that place, but we don't know if that positive displacement is dropping down to zero or what it's doing. So we're going to have to do something to figure out some more information. One thing we might do is take the derivative of this thing with respect to time. And that'll tell us whether or not the thing is going up and down at that particular time and place. So let's see. Could we do that? Or we could also we could look at that and see what the magnitude of this happens to be. And yeah, we know that the cosine function will have its maximum upward displacement when its argument is equal to, let's see, 0 or 2 pi or 4 pi and so forth. And you can tell that by looking at the graph of it here. Well, we're concerned with where it is here at that particular thing. So this isn't going to change, but this will change as time goes by. But let's go ahead and figure out what that magnitude of the argument here happens to be. It'll be 7.00 times 10 to the minus 2 meters times the cosine. At this time, it'll be the cosine of whatever all that stuff came out to, 19.6 times 0.36 plus okay, and I get a value of let's see, 30.0 or 30.6, and it would be dimensionless. Okay, now how's that look on a radian graph? 30.6 is equal to, take a few 2 pi's here. Get that. 4 pi is 12.6 or 12, yeah, per pi we can multiply, give as many sig figs as we want. 6 pi, 8 pi, 10 pi. I think we're going to be out between 8 pi and 10 pi, so let's just figure those out. 0.1. And 10 pi is going to be 31.4. So it's in between those two things, 8 pi and 10 pi. And we want to know how long it'll be from whatever that time was before we get that. So we're still going to have the 19.6 meters to the minus 1 times x, which was 0.360 meters. But we're going to be adding to that 157 seconds to the minus 1 times some t that we don't know. And that product is going to have to equal 31.4. And that's dimensionless. So actually, that's not a bad equation to solve. I just take this away from it, divide by 157. It'll tell me what the time is at that time. And then I'll subtract the time that they gave us there, the 0.150 seconds. Okay, kind of complicated. So take 10 pi minus this is really just an arithmetic problem now. I get that. Let's see. Not much. Oh, I have to divide by e. Or 157. Okay, and I get 0.155 seconds is the next time that'll happen. Well, how much longer was it after the 0.150 seconds? It's just 0.005 seconds. So I'll call this T max for when it's next at the maximum. So T max minus T is going to be 0.155. Sorry, this is so messy. Minus 0.150 seconds, 150 seconds, or 0.005 seconds. So that's how much longer after the thing we studied in part C that it'll take for it to reach the maximum. So not that long. Okay. Well, that was kind of a hard one with lots of different math, but the individual parts, you're just playing with an equation. Okay. Something they discuss in section, I think, 15.4 is the wave speed on a string. And again, that's something you could either do it experimentally or you could solve some more math that we don't have access to, a differential equation, but they kind of do a sketchy development of this equation. Anyway, in this case, F is equal to the tension in the string. And mu is what they call the mass density of the string. A string is supposedly only one-dimensional. It's the mass per unit length of the string is what it happens to be. And we'll use that in a little bit, but on some problems. In fact, we'll use it in a lab next week and look at standing waves on strings, and it's kind of fun. And then it's got the average power delivered by a wave, and that would be in watts, but 1/2 the square root of mu times F. So instead of F divided by mu, it's mu times F, and then times omega squared A squared. And this is just true for waves on strings where you have something like that. It says mechanical waves, but there are other kinds of mechanical waves that don't have a stretch string. So that's maybe a little too broad a statement. It looks different for things like sound waves and stuff anyway. But for electromagnetic waves, power doesn't depend on the frequency, so there wouldn't be an omega in an electromagnetic wave. This is one of the problems out of the book, and I don't remember the number of it, an early one, but it's talking about ultrasound. And ultrasound is just a name we give to frequencies that are above what a human can hear. And broadly speaking, it's above about 20,000 hertz. Now, I can't hear frequencies that high anymore. You lose up frequencies with age. I try to be pretty careful about my hearing whenever I'm using a power tool. I'll stick on headphones or earplugs to protect my hearing, but still it's a lose. Last time I checked, we've got some oscillators in the classroom that we can hook up to one of the gadgets we've got. Anyway, and you can make sound of different frequencies. I could hear up to about 13,000 hertz, which when I actually listen to it, I think, I don't need to hear that frequency. It's a really high thing, and it's quite a bit, well, it's about an octave lower than 20,000 hertz, but there isn't any note that I want to hear that's up that close. So I don't feel that bad about not being able to hear up to 20,000 hertz anymore. I don't know if I ever could, actually. I never tested it when I was younger. I used to be able to hear up to 17,000 hertz. I know because the old style of TVs, the kind that had a cathode ray tube and were really deep, and I don't know if any of you have ever seen one of those anymore, but they put out a whine that was at like 17,100 hertz or something, and I could hear that when I was a kid, and it was something you could hear. But anyway, ultrasound is just frequencies above there. Waves above it can be used to penetrate the body and produce images by reflecting from surfaces. And in a typical ultrasound scan, the waves travel at a speed of about 1,500 meters per second. By the way, it's an interesting thing. Sound waves travel slower in air than they do in water, and they travel fastest in a solid. I can remember, I don't remember what grade I was in elementary school in Spokane, but our teacher demonstrated this to us. There was a long chain link fence along one side of the playground, and she sent a kid down to one end of the fence with a rock and had him slam the rock against the fence, and you could hear the sound come through the air, but before it came through the air, you could hear the sound wave that traveled down the metal pole of the fence to you. It was maybe, I don't know, 50 yards away or something like that, and there was a noticeable gap. So the sound goes faster through a solid than it does through the air. Okay, so anyway, we've got a wave speed of 1,500 meters per second. And to get a detailed image, you want the wavelength to be no more than 1.00 millimeters. That means you want F lambda here, and lambda you want to be 1.00 times 10 to the minus third meters. Okay, so what do you want for the frequency? Just do the math. Here you've got 1.50, or just 5, we'll call it, times 10 to the third meters per second, and we're dividing by 1.00. Oh, actually, it's only 2 sig figs. 1.0 times 10 to the minus third meters, and you end up with 1.5 times 10 to the sixth per seconds, or hertz. So that's 1.5 capital M, that's for 10 to the sixth, megahertz is what that sound happens to be. So no way you're going to be able to hear that with your ears, but that's a typical frequency for an ultrasound. So they might use higher frequencies now. I don't know. They are much more detailed than they used to be. I know that. Okay, let's see. Here's another one with a wave equation. And this one's just kind of plug and chug on this. We have a certain transverse wave described y of x and t is 6.50 millimeters, cosine of 2 pi times this stuff. And this is the way things are written sometimes, where you'd have the cosine and then you'd have a 2 pi outside of here multiplying this other stuff. So something you could say from this is that, well, first thing it asks for is the amplitude. That's the amplitude, 6.50 millimeters. So we can say that. The wavelength, the wave number, well, let's rewrite that cosine function here first. You'd have the cosine of 2 pi divided by 28.0 centimeters times lambda. That's K. That's the K value. And then you'd have minus, distributing that 2 pi through there, you'd have 2 pi divided by 0.0360 seconds times t. Well, here's K, here's omega, and you can pull off a couple of things like this. We know the amplitude, the wavelength, K, is equal to 2 pi divided by the wavelength. Well, K is equal to 2 pi divided by 28.0 centimeters. So we didn't even have to do any work to figure this out. The wavelength is just 28.0 centimeters. And then this thing, omega, is 2 pi divided by the period, but omega is 2 pi divided by 0.0360 seconds, so the period is 0.030 seconds. So that part wasn't too bad. Then the speed of propagation. Well, that we have to do a little bit of work to get. So let's see, we know the wavelength. If we take the reciprocal of that, we'll have the frequency. Although, since V equals F lambda, you could also write V as lambda divided by the period. So that'd be easier. We'll have 28.0. I'm going to write that as times 10 to the minus 2 meters. So I think this is going to go at a pretty good clip. Divided by the period, 0.0360 seconds. And the wave speed here, turn on calculator first. You guys are probably already done with this. Oh, I get about 7.78 meters per second. So there. Oh, and the direction of propagation is the last thing. Well, remember, if it's got a minus sign, it moves in the positive x direction. If it has a plus sign, it's going in the negative x direction. So all of those things we could figure out without a whole lot of work on that problem. But just introduce a wave equation and getting a little familiar with some of the mathematics of it. Okay, here's one maybe a little more interesting. We have a 1.50 meter string of weight 0.0125 newtons tied to the ceiling at its upper end, and the lower end supports a weight W. And we're going to neglect the very small variation in tension along the length of the string produced by the weight of the string. If you have a string that's attached to something, like here's some firm support, and you've got a rope that's hanging down there, the top of the rope has to support the entire weight of the string. And so the tension at the top will equal the entire weight of the string. Whereas when you get down here an inch above the bottom of it, the tension there only has to support that bottom inch. And so you'll have a continual variation in tension between the top and the bottom. But in this case, we're told to ignore that variation in tension. And that's because whatever the weight W is, it's probably a lot more than 0.0125 newtons. In fact, we're going to figure it out. And so the weight of the string isn't going to matter a whole lot. Okay. So, what else? When you pluck the string slightly, the waves traveling up the string obey the equation y of x and t equals 8.50 millimeters. So that would be the amplitude times the cosine of 172 meters to the minus 1 times x. So that would be k, 172 meters to the minus 1. And then minus 4,830 seconds to the minus 1. There's omega. And in this problem, x is the vertical direction and y is horizontal. So doing that. Assume that the tension of the string is constant and equal to W. So we have that. How much time does it take a pulse to travel the full length of the string? Well, let's see. It was 1.50 meters long. We can figure out the speed of the wave if we look at these two things. And remember, k is 2 pi divided by the wavelength. And in this case, it's equal to 172 meters to the minus 1. Omega is 2 pi times the frequency, and it's equal to 4,830 seconds to the minus 1. And what did we figure out? Omega divided by k, I think, is going to equal 2 pi times the frequency divided by 2 pi divided by the wavelength, and that ends up equaling frequency times wavelength, which is v. Otherwise, you could have actually solved this equation for lambda. Lambda is going to equal 2 pi divided by 172 meters to the minus 1. Solve this equation for frequency, and then just multiply them out. But I'm just going to take omega divided by k, do it in one calculation. So 4,830 seconds to the minus 1 divided by 172 meters to the minus 1. And you'll actually end up with meters per second here. And I'm writing too big to be able to get all these parts down, as usual. Whoops, I didn't want to do that. I get about 28.1 meters per second for the wave speed. So the first question was, how much time does it take a pulse to travel the full length of the string? Well, this is just a distance equals rate times time thing now. The distance it has to travel is 1.50 meters. So D equals VT in this case. So the time is going to be the 0.150 meters divided by 28.1 meters per second. And whoops, it's supposed to be 1.50. Okay, and I get about five, or let's see, we can keep 3 sig figs, I guess. 5.34 times 10 to the minus 2 seconds. That's what it would be. Okay. What is the weight W? Right? Well, it's the weight that you have hanging from this thing that's going to produce the tension in the string, and the speed of the waves in the string, do it here, V is that formula that I gave you on the other page. It's the tension, whoops, the force in the string. It's an F over mu. By the way, I can't remember. I used to teach this course, which was a survey of physics, and it's below an algebra-based course. It was kind of conceptual physics, but in the book for that, they used the formula tension divided by, they didn't use mu. I think they used the Greek letter rho. And so if you see me write it like this, it's because I'm still thinking in terms of that class. But anyway, we'd have the weight W, and then we would take the, oh, we have to figure out the mass of the string, not the weight. So the weight of the string, which is going to equal its mass times the acceleration due to gravity, is 0.0125 newtons. So the mass is going to be not much. So then I'm going to be out of room on the page before too long. Whoops. Boy, did I hit a wrong number. Okay, the mass will equal, yeah, 1.27 times 10 to the minus third kilograms, or 1.27 grams. So this, not much to the string there, but that's over a length of 1.50 meters. So mu, that mass per unit length, will equal 1.27 times 10 to the minus third kilograms divided by 1.50 meters. Okay. I was thinking too many steps ahead. Okay. So mu has a value of 8.49 times 10 to the minus fourth kilograms per meter. Okay. So W divided by mu is what we'll go into the radical here, but I'm going to square both sides of this and solve for W. W will equal, when you square both sides, you'll get V squared, but you'll just have a mu there. So it'll equal mu V squared. So there's our mu value. 8.49 times 10 to the minus fourth kilograms per meter. And I'm going to be multiplying that by V. Did I figure that out somewhere? Oh, 28.1 meters per second. I guess I figured it out and never, oh, there it is. Okay, so let's see what we're going to get here. I get about 0.671. And this would be, let's see, meters squared per second squared. Divided by meters, I'd have kilogram meter per second squared, which are newtons. So that's what I'd have for the hanging weight. And okay, so 0.671 versus 0.125 newtons. This is, I don't know how many times that. Okay, this is about 54 times as heavy as the string itself. So I think we're probably justified in ignoring the variation in tension of the string, or variation of tension due to the weight of the string. It could be a complicated problem if you had to deal with that, because the wave speed would be varying continually as you go up the string and becoming faster as it goes up there. Oh, let's see. What else were we supposed to figure out? Oh, one question it asks, question D, what's the equation for waves traveling down the string? Well, you just take the equation for waves traveling up the string and change this minus sign to a plus, and you have that. We never did actually figure out the wavelength of these things, so let's go ahead and do that. That'll be about the last we have time to do today, I think. Oh, let's find a blank sheet somewhere. Okay, K was 172 meters to the minus 1, and that's 2 pi divided by lambda, or the wavelength is going to be 2 pi divided by 172 meters to the minus 1, or pretty short, I think. Yeah, I get 3.65 times 10 to the minus 2 meters, which is 3.65 centimeters. So I don't know, about 1.5 inches, something like that. Let's see. Yeah, and dividing by meters to the minus 1 gives you units of meters. So we know that. But the question asks, how many wavelengths are on the string at any instant in time? Well, if it's got a length of 1.50 meters, you can think of that L equals 1.50 meters is going to equal some number of wavelengths, and that number C, I shouldn't use C because we use it for the speed of light, but I'm going to anyway. Anyway, 1.50 meters divided by the wavelength, 3.65 times 10 to the minus 2 meters, and we'll get about 41. So about, and there's a little bit left over, but that's close enough. So 41 waves would fit on there. Okay, well, that one had quite a bit to it. What else? Got a piano wire and a horizontal wire stretched, but those are not too bad. And these are problems that are on the handout that I'm going to post here shortly. And I think you'd be able to do those if you printed them off and tried them out on your own. In fact, it's not a bad thing to do, is to print that off and try the problems on your own. See if you can just do them by yourself. And good practice. You've already seen them done, but see if you can generate that. And I'll also suggest some problems in the book. I think I came up with a couple already anyway. Okay, it's been taking a long time for some reason to upload stuff to YouTube, and I don't know why, but I hope to have it up there by 2 o'clock. Sometimes I've been able to have it done by 1:30, but it's just been kind of stalling on part of the process. And so if you want to watch this video again, it may take a while. So please be patient. Okay, I'll stop the recording.